Hi. In this set of lectures, we're going to talk about something called Lyapunov functions. Now what Lyapunov functions are is they're functions that really can be thought of as mapping models into outcomes in the following way. So what we can do is we can take a model or take a system and we can ask ourselves, can I come up with a Lyapunov function that describes that model or describes that system? And if I can, then I know for sure that system goes to equilibrium. So what a Lyapunov function is it's this tool, it's this incredibly powerful tool to help us understand, at least for some systems, whether they go to equilibrium or not. Let me explain what I mean a little bit more. Remember how we talked about there's four things a system can do. It can go to equilibrium, it can cycle, it can be random, or it can be complex. Lyapunov functions, if we can construct one, and that's going to be one of the challenges, if we can come up with one, then we'll know for sure that the system's going to go to equilibrium. If we can't construct one, then maybe it goes to equilibrium, maybe it's random, maybe it's chaos, maybe it's complex. We don't know. We can't really say anything. So the challenge here, the really hard and fun part, is coming up with Lyapunov functions. If you come up with a Lyapunov function, then you know for sure, hey, this system's going to an equilibrium, which is a nice thing to know. Not only that, we'll see in a minute, that you can see how fast it's going to go to an equilibrium. So how does it work? Here's the idea. Suppose you have a system, and I've got something I care about here, which might be velocity on this axis. And suppose there's a minimal velocity, which is 0, which I'm representing by this big black region down here. Now suppose what I say is the following property holds. I start with some positive velocity, and every period, if the velocity changes, it goes down. So it's going to go down to there, and then it goes down to there. Now it could be the velocity doesn't change. Well, if the velocity doesn't change, then you're fixed. Then you're in an equilibrium. But if the velocity does change, it has to go down. Well, if that's the case, if it changes, it has to go down. At some point, it's going to hit this barrier down at the bottom, the zero velocity point. And when it hits 0, it has to stop. So that's the idea. If it falls, if it moves, it has to fall. That's property 1. It's got to go down. If it moves, it's got to fall. And there's a minimum. Well, those two conditions are going to mean that the system has to stop. With one little, we got to pick up one little peculiar detail besides that. But that's basically the idea. If the system is going to move, it's got to fall, and there's a min. So therefore, at some point, it's either going to stop before the min, like it might fall, 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 and then stop right here, or eventually it'll hit the thing at the bottom. That's the idea. Now, how do economists do it? Economists do the opposite. They have something where maybe this is happiness on this axis, and maybe people are making trades, and you say people trade, happiness goes up. So I've got a happiness here, people trade, it goes up, people trade, it goes up. So anytime people trade, total happiness goes up, otherwise they wouldn't trade. So that means anytime the system moves, happiness is increasing. But you've got this caveat that there's a maximum happiness here. It can't go above this black bar. So what does that mean? If anytime people trade, it goes up, and at some point you're going to hit this bar, that means the process has to stop. And if it has to stop, that means it's in an equilibrium where there's no more trade. Everybody's happy with what they've got. So there's these two, in some sense, identical ideas, right? One is from physics, that if things fall every period and there's a min, the process has to stop. And then from economics, you have if things go up every period and there's a max, it has to stop. That's it. That's the theorem. I know it sounds sort of frightening, right? Lyapunov. It sounds really scary. And I'm sure when you looked at the syllabus, you thought, oh my gosh, Lyapunov functions. This is going to be hard. Maybe I'll skip this lecture. I thought about calling it Dave functions or Maria functions, because then it wouldn't sound so frightening. If I said, we're going to study Maria functions, you'd all say, oh, that's probably going to be pretty easy, or Dave functions. It's just that with these Russian surnames, you sort of think, oh my goodness, this is frightening. It's not. Very, very easy. Here's the formal part. What we do is we say there's a Lyapunov function if the following holds. First, I just have some function f, and I'm going to call this a Lyapunov function. And there's just 3 conditions. The first one is it has a maximum value. I'm going to do the economist version. In the physics version, I'd say it has a minimum value. So it has a maximum value. Second assumption, there is a k bigger than 0. So there's some number k bigger than 0, such that if xt plus 1 isn't equal to xt, so what that means is if f is going to basically map the state now to xt into xt plus 1. If they're not equal, right? So if the state in time t plus 1 is not equal to the state at time t, then f of xt plus 1 is bigger than f of xt plus k. What does that mean in words, not in math? What it means is if it's not fixed, so if the point is not fixed, then it increases by at least k. just by some fixed amount. It doesn't always have to increase by exactly k. It can increase by more, but it's got to be increased by at least k. If those things hold, so it's got a maximum, you're always increasing by at least some amount k, then at some point the process has to stop. Because if it didn't stop, it would keep increasing by k and it would go above our maximum. That's the theorem. Now what is this assumption to? What is this thing about it's got to, before I guess it has to be bigger, now I've got it's got to be bigger by plus k. What's going on? Well, this goes back to something way back in philosophy called Zeno's paradox. And Aristotle's treatment of this is probably the one most of you learned in college. And that is, suppose I want to leave this room. Suppose I'm going to leave this room right here. And the first day, I'm standing right here. Here I am. Da, da, da. And the first day, I go halfway to the door. Then before I get and then the next day, I go another halfway. And then the next day, I go another halfway. The next day, another halfway. The next day, another halfway. I'd never actually leave the room. Well, if I don't assume, because what's happening here is I'm going up a half, and then a quarter, and then an eighth, and then a 16th. So if I made my steps smaller and smaller and smaller and smaller and smaller and smaller and smaller, it could be that I continue to increase, but I never actually get to the maximum. But if instead I assume that each step has to be at least 1/16th, well then after 16 steps, I'm going to be out of the room. So what Zeno's paradox is that you can basically keep making steps halfway and you'll never actually exit. And the paradox was that you could keep moving towards the door but never actually get to the door. The way we get around that is we make this formal assumption that says there's some k such that if you move, you go up by at least k. And so in this case, I talked about it being 1/16th. If you go up by at least 1/16th, then in 16 steps you're out of the room, and since you can't leave the room, that's a max, what's going to happen is the process has to stop. So that's all there is to it. The Lyapunov function consists of is f, it's got a maximum value, and then there's some, if it's the case that the process moves over time, then in the next period, you've gone up by at least some amount k. And since there's this max, and you're going up by at least k each time, eventually you're going to hit that max, and the process has to stop. Now there's a bonus that we just got as well, right? If each time I go up by 1/16th, then in 16 steps, I'm going to have to stop. So you can also say how fast the process is going to stop, and that's obviously not a very complicated calculation at all. Here's the tricky part, though, I talked about this. The hard part about this is constructing the function. So the theory, the idea that there's a function, there's a max, we go up by k each time, that's really straightforward. The really tricky part is going to be coming up with a Lyapunov function, coming up with that function f. So what we're going to do in this set of lectures is we're going to take some processes, things like arms trading, trading within markets, people deciding where to shop, and we're going to show how in some of these cases it's really easy to construct Lyapunov functions. In other cases, it's really hard to construct Lyapunov functions, or maybe we can't even construct Lyapunov functions. So we're just going to explore how this framework, this Lyapunov function framework, can help us make sense of some systems, and help us understand why some things become so structured and so ordered so fast, and why other things still seem to be churning around a little bit. So the outline of what we're going to do is we're just going to start out by first doing some simple examples, seeing how Lyapunov functions work. Then we're going to move on and see some sort of interesting applications of Lyapunov functions, maybe when they don't work. And then from there, we'll go on and talk about processes that maybe we can't even decide whether Lyapunov functions exist or not. Some open problems in mathematics that involve trying to figure out, does this thing go to an equilibrium or does this thing continually churn? And then we'll close it up by talking about how Lyapunov functions differ from Markov processes. Because remember, Markov processes also went to equilibria. And we'll talk about how those equilibria are different from the equilibrium we're talking about in these Lyapunov functions, and also how just the entire logic about how the system goes to equilibrium is different in the two cases. Okay, so let's get started. Thanks.